Hey guys, I hope everyone's studying well for the finals. So before the finals, actually a few hours before the finals, I would like to talk about one of the questions in exercise 4.2, question 7, part J of Greenberg textbook. It is about using the Frobenius series to solve the equation y prime prime minus x cubed y is equals to 0. The usual equations that we see that can be solved by Frobenius series is of the form x squared y prime prime minus y. In that case, we can just use the ensemble y equals to x to the power of n, and this will work out very well. But in this case, we can't exactly use it. So I'm going to go through how to solve it. Let's try the ensemble y equals to xp summation an x to the power of n. Why did I choose not to use summation an to the times x to the power of n? It's because I tried it and it only gives me one linearly independent base. In that case, it wouldn't work. So this is kind of like p set 5, one of the questions in p set 5, and it seems like we have to use the ensemble x to the power of p in front. So with this ensemble, we get the following value for y prime prime. It is a summation n plus p minus 1, an x to the power of n plus p minus 2. And for the second term, negative x cubed y, we get the following. Negative an x to the power of n plus p plus 3. But there's a problem. The powers of x's do not exactly match up. Here you get n plus p minus 2, here you get n plus p plus 3. We have to match up the powers. So one option that we have is to reduce the power of the negative x cubed y term to match x to the power of n plus p minus 2. To do this, we realize that we change the summation limit to start from 5 and negative an minus 5 x to the power of n plus p minus 2. But there's one more problem here. The initial value of the summation term is different. Here it starts at 5, here it starts at 0. To do this, we define that a to the power of negative 5, and basically a with indices that is less than 0 will be 0. And therefore, negative x cubed y term will become summation from 0, negative an minus 5 x to the power of n plus p minus 2. Yes, right now, both the powers of x's matches up, and the summation initial values matches up as well. We can combine both terms according to the equation and get the following. In order to solve for p, we set n equals to 0. In which case, it gives us p times p minus 1, a naught is equals to 0. Assuming that a naught is not equals to 0, if not the solution will be trivial, we get p equals to 0, 1. And therefore, we can re-express y in the form of summation an x to the power of n plus summation bn, which is a new set of coefficients, x to the power of n plus 1. Here, xn and xn plus 1 are linearly independent bases. And therefore, let's find out the coefficient values for an. An is equals to n minus 5 over n minus 1. And in that case, we change the n value indices once again, so that an plus 5 is equals to an divided by n plus 5, n plus 4. And for bn's, we do the same and realize that bn plus 5 is equals to bn divided by n plus 6 over times n plus 5. And in that case, since we have both coefficients and the y values, we basically solve the equations. Thank you.